Alright, so this lecture is called Nature of Solids. So let's just kind of refresh for a moment. Let's say we were looking at three molecular windows. What that means is you could zoom in and you could see the actual particles in a solid, a liquid, or a gas. In a gas, we know that the particles are pretty far from each other. They're never really close to each other to exhibit any kind of attractive or repulsive forces. They just keep colliding and changing directions. That's how gases would behave. Liquids, right, are a little bit different. Liquids are much closer because they have intermolecular forces, and they're still able to move. They can slide past each other, but they need a lot more energy if they want to escape into a gas. So while they're liquid, they have kinetic energy. They have less kinetic energy than gas, but they're able to slide past each other. They can move around still, but they're just very close to each other. But now it takes us into solids. Solids are much more attracted to each other, the particles. So they're so attracted to each other that they're not allowed to move from where they are. They're in what's called fixed positions. So if we zoomed in on them, you can kind of think of them like this. They're sort of these 3D stacks of solid particles, and they're all very, very attracted to each other. So they can't move. Now, that doesn't mean they're not moving at all. It doesn't mean they're like just completely frozen. On a molecular level, even frozen things like ice, the atoms that make it up are still moving. The atoms on the surface of your screen are still moving. The atoms on your table in the kitchen, they're still moving. They're just locked in position. So really all that they can do is sort of wiggle. That's it. They wiggle, they move. And you can test it out if you put both hands flat down on your desk, and then if you knock on with one hand, if you knock on the table, your other hand is going to feel, because as you knock on one side of your table, all these atoms are going to vibrate and send that energy to your other hand that's on the other side of the table. So we know that these atoms can move. They just don't move from the fixed position that they are in the crystal systems. Alright, so we've got solid particles, and these solid particles are in fixed position. Their intermolecular forces are so strong that it's very hard for them to leave each other. They need a lot of kinetic energy, and the only way that you can supply enough kinetic energy is by heating it. I'm going to use red instead. Is by heating it. When you heat it, these particles, they start vibrating. They start vibrating very, very quickly. And if they gain enough heat and they vibrate just enough, some of these particles will then be able to kind of move out of their position. And as they move out of their position, they're still kind of close to the other particles, so there is attraction, but they're able to slide past them. Well, once these particles start sliding around, but they're close to each other, we no longer have them existing as a solid. What we've done is when we heat up solids with a sufficient amount of energy, we've turned them into liquid. So, going from solid to liquid is called melting, which you know. Now, if we did the reverse, if we took liquid particles and instead of heating them, we lowered the temperature, well, the particles would start slowing down. They wouldn't be moving around as much. The kinetic energy would be dropping. They wouldn't want to move anymore, and then they sort of form just this solid position, or solid state, which is called freezing. Of course, the temperature at which a solid turns into liquid is called a melting point. Well, ionic solids have very high melting points because the attraction between the ions is extremely strong. So, for example, if we had a sodium ion and a chloride ion, so sodium chloride, one is positive, one is negative, their attraction is so strong that it takes a huge amount of energy for it to melt. In fact, it would take a rather high melting point of 801 degrees Celsius to get table salt, right, which you put in on your fries. It would take that much heat, or that great temperature, for it to melt into liquid and have liquid salt. Now let's compare that to, say, molecular solids. Those molecular compounds typically don't have very high melting points. They usually have lower melting points, and I'm just going to put MP for melting points. So an example of a molecular solid would be water, and I know you're thinking, wait, that's liquid. I mean specifically solid water, which is ice. Now, ice does have a melting point. At what temperature does an ice cube start to melt? Well, if the freezing point of water is 0 degrees as it goes from liquid to solid, then the melting point is the same temperature. Water, ice, will melt at a temperature greater than 0 degrees Celsius, right? I mean, our room temperature is usually about 20 degrees Celsius, and water naturally exists as liquid because we are above its melting point of 0 degrees Celsius. But if we were below 0 degrees Celsius, it wouldn't melt. It would stay as solid. So the main thing to remember is that ionic solids have high melting points, right? If they're made up of ions, it's going to take a lot of energy around the system for it to melt. If it's a molecular solid, where they're not attracted by the charges of the ions, but instead by covalent bonds, well, then we don't need as much of a great temperature in the surrounding environment. Of course, some things you could heat up, for example, say wood, right? If you were to heat up wood, or you were to heat up, say, sugar cane, right? Unfortunately, wood and sugar cane don't melt. As you heated them, they're much more on the molecular side than they are ionic. So as you heated them, they would actually break down into other substances before they ever exist as liquid. So there's no such thing as liquid wood or liquid sugar cane. Sorry about that. All right, now let's talk about the most important concept in this section, which is called crystals. As it turns out, most solids on Earth are crystals. There are atomic crystals, molecular crystals, ionic crystals, covalent crystals, metallic crystals, and as weird as it might seem, you don't have to get too concerned. All a crystal means is, if you zoomed in on the particles in a solid, they would be following this repeating pattern over and over and over. That's what a crystal is. A crystal is a substance whose atoms or ions or molecules that make up that solid substance are arranged in an orderly, repeated, three-dimensional pattern. And that three-dimensional pattern is called a crystal lattice. So let's take, for example, probably the most common crystal we can think of. Sodium chloride, NaCl. Here we have tiny, tiny, tiny crystals of sodium. Now if you look really closely, can you see the common shape that the sodium crystals are taking? So they kind of look like a square, or if we're talking about 3 dimensions, we're probably looking at a cube shape for this crystal. And that's the case for sodium chloride. It turns out that when they form solids, they space out in a way in 3-dimensional space that gives us what we see on a macroscopic level, right, or normal for us, this repeating pattern gives us this cubic shape. So the sodium chlorides have what's called cubic crystal shape. And you have to be kind of familiar with the different types of crystals that there are. Now, luckily, there are only 7 that we have to be aware of, because all crystals fall under 7 categories of crystals. And here they are. Now, lucky for you, you don't have to memorize all these little bits of information about all those crystals. I'm going to explain to you how it works, but you do have to know the 7 types of crystals. So we'll start with the very first one that we mentioned for sodium chloride, simple cubic. So cubic, all that means is that all the sides are the same length, right? So A, B, and C are all the same length. And these symbols you see here are Greek letters, alpha, beta, gamma. Those represent the angles inside of your cube. Well, we know that in a cube, all the angles are the same, and all the angles are 90 degrees. So sodium chloride is an example of a cubic crystal. Another example of a cubic crystal is this mineral right here. Now, you can kind of see it. You can kind of see these cube shapes that are forming down here. You see that cube shape. Now, are they perfect cubes? No. And the reason that they're not perfect is because they're exposed to the environment. They're exposed to weathering. They're exposed to rain, erosion. Their surfaces sort of get smoothened out. They're not perfect cubes. But under perfect conditions, we would see these nice, perfect cube-shaped material. Now, what's nice about minerals is that because they have planes of atoms all like bonded to each other across a surface, that when they're very easy to cut, because if we were to zoom in on the surface, all the atoms would be bonded sort of in a row. So when people cut minerals, they basically hit a plane of atoms that are all on the same surface, and then we get this nice cut. That's what makes cutting minerals for your jewelry very easy. Now, this mineral that we have here is called galena. It's important to remember that. And the next crystal shape is called tetragonal. So it looks very similar to cubic. The only difference is, in cubic, they got 2 sides the same. Now for cubic, all 3 sides are the same. But for tetragonal, one of the sides is the same. That wasn't very obvious. One of the sides is different. So in tetragonal, 2 sides are equal, A and B are equal, but they are not equal to C. One side is different. Now, it's still a rectangular prism, so it still has internal angles of 90 degrees. So anytime you have a crystal that has 2 sides the same, one side different, and all the internal angles are 90 degrees, it is tetragonal. An example of tetragonal crystal is what you see here. This crystal is called wolfenite. Now, it's not always obvious because these minerals are exposed to the environment. But you can kind of see it right here. You've got 2 sides that are the same, you got that square face, and then you've got one side that is not the same. So that's an example of a tetragonal crystal. The third kind of crystal is called orthorhombic. So it looks similar to the simple cubic and tetragonal, but we have something different. So let me repeat. For cubic, 3 sides are the same. For tetragonal, 2 sides are the same and one side is different. For orthorhombic, one side is different, then the other side is different, then the other side. All 3 sides are different, but all the angles are still 90 degrees. An example of that would be this crystal here, which is called topaz. Again, not as obvious. I can't even draw it here, and I won't. And again, you can't just look at a crystal and immediately know what kind of crystal system it is. But topaz is orthorhombic. Now those are the easier ones. Now let's start looking at the harder ones. Let's look at rhombohedral. In rhombohedral, what do you notice about the sides? A is equal to B is equal to C. What that means is all the angles here, all the sides here are the same. They're all the same side. They're all the same length. But what's different is all the angles. The angles are all equal to each other, but they are not 90 degrees. That's what gives this cubic-ish crystal. Actually, it kind of looks like a distorted cube, like if you took a cube and kind of forced it outward in an angle. So this distorted cube-like substance is called rhombohedral. So here you have that image. Again, not obvious, but you kind of see that angular cut that's not exactly 90 degrees. But it kind of has a cubish feel to it. This is an example of calcite. Calcite is a rhombohedral crystal. Now let's look at, we're going to go ahead and do these two together. Monoclinic and triclinic. So in both of these cases, what they have in common is their sides are not equal to each other. So one side is one length, another side is another length, and a third side is a different length. Same thing for a triclinic. Right? You've got one length that's not equal to another length that is not equal to another length. And another thing that they have in common is that there are some angles that are not 90 degrees. Not 90 degrees. Not 90 degrees. One way to kind of help you remember this is that for monoclinic, one angle is not 90 degrees. For triclinic, none of the three angles are 90 degrees. For monoclinic, two of the angles are equal to each other and they are 90 degrees. And again, it's hard to just know this by looking at the crystals in nature. Alright, I just realized I made a mistake, and I'm 17 minutes in, so I am not going to go back and re-record this video. So let me just go ahead and address that right now. This that we saw just right now for rhombohedral, this is not calcite. Calcite is actually this one right here. Okay, so here is the one that you can tell, yeah, it kind of looks like a cube, but it's distorted just a little bit. Again, kind of like a cube, but a little bit of distortion. This one, my apologies, this one is calcite. Now let's take a look at monoclinic and triclinic. Surprise, these are the ones. This one right here, even though it looks very similar to calcite, which can be confusing, this is actually called gypsum. So gypsum is monoclinic. Again, not easy to tell, but none of the sides are equal to each other, and it's kind of hard to identify the sides. If you were to do the whole big one, there's one side of one length, one that's a different length. We don't have the depth to kind of see the other length, but they wouldn't be equal to each other on a molecular level. And some of the angles are 90 degrees, two of them are 90. Alpha is equal to beta is equal to 90 degrees. But since this is monoclinic, one of the angles, which we'll just represent with gamma, is not 90 degrees. This is an example of a monoclinic crystal. If we look over here, this is called amazonite. So it's a nice pretty color. Amazonite is an example of a triclinic crystal. So, and again, I can't even point anywhere to draw here, but this triclinic crystal, if we zoomed in on the molecules, the lengths between them would not be equal to each other, and none of the angles would be equal to each other, nor would they be 90 degrees. So this is an example of a triclinic crystal. And finally, we're left with hexagonal. So, for hexagonal, it's usually very obvious to identify it on a molecular level. Hexagonal, two sides are equal, one is not. Two angles are 90 degrees, and one is 125 degrees. So you kind of have that 125 right there. And it looks confusing, but hexagonal is called hexagonal because you've got this sort of hexagon shape here. But really, it's just a combination of three of these four-sided shapes, right? You have one here, you have another one here, and then you have another one here. So the three together sort of make up this hexagonal shape. And here we have an example of that. This mineral that we see here is called tourmaline. So not the most obvious, but if you look at it, you can kind of see that it's going to have that hexagonal feel to it. I might not have drawn the hexagon shape very well, but it's kind of there. So let's say we zoomed in on sodium chloride. So here our sodium ions are represented by the little purple spheres, and our chloride ions are represented by the green spheres. So if we zoomed in, all we would see is just this repeating pattern of sodium chloride, sodium chloride, sodium chloride, sodium chloride, dot, dot, dot. Well, the formula for sodium chloride is the smallest whole number ratio of sodium ions to chloride ions, which is why it's called NaCl. But how do we land on the cubic shape? Well, these shapes that we're talking about come from what are called unit cells. By definition, a unit cell is the smallest shape, it's the smallest group of particles inside of a crystal that keeps some kind of geometric shape, and that is called the unit cell. So basically, if we were to take a sodium ion and make it a corner of a cube, right, or a cell, then this right here would be the smallest ratio, and I'm probably using a bad color because the lines here are red. I'll use a different color. This would be the smallest collection of ions that still keep some kind of geometric shape, in this case cubic. Now some solid substances can exist in more than one form. Probably the best example would be carbon. Actually, let me use a thicker color. Carbon. Carbon can exist as diamond, which this carbon crystallizes to look like a diamond when it's under a tremendous amount of pressure. But it can also exist as graphite, if you remember from another lecture. Graphite is actually the pencil lead that you write with. That's just carbon. In fact, there's even this crazy substance, very weird, it was discovered back in the 60s, called a Buckminster fullerene. Actually, no, it was discovered in the 80s. And it's called the buckyball for short, and its formula is C60. So it's also just made up of nothing but carbon atoms. And even though all three of these things are made of the exact same thing, which is carbon, their properties are different. We know that for diamonds, they are extremely dense, and they are extremely hard. In fact, on the scale of hardness for minerals, it is considered a 10. It's the top. It's the hardest thing that we know on that list. Now, if we consider graphite, graphite is not very dense, right? So it's low density, and it's very brittle, It's very soft. And buckyball has other properties. Well, there's a name for substances that have different forms in the same physical state, and this term is called allotropes. So there are different allotropes of carbon. So it makes them different the way the atoms are arranged. The atoms in diamond are much closer to each other, and I believe that diamonds have a cubic crystal structure. The pencil lead, graphite, has hexagonal structure, and the buckyball here, it's a three-dimensional shape. It doesn't have one. It has like a weird name called truncated icosahedron, something like that. That doesn't matter. Don't worry about that. All right, the next thing we're going to talk about is amorphous solids. Now, there are two kinds of solids. There are crystals, where we know the particles are in repeating patterns in three-dimensional space over and over and over. You could literally cut out part of the molecules and just copy-paste and get the whole crystal. But then we have the new type of solid, which is called amorphous. And anyone who knows their Latin roots knows that means not or no shape or form. What that means is if we could zoom in on molecules in an amorphous solid, the particles are not arranged or bonded in any kind of repeating pattern. There's no organization. They lack internal structure. All right, so three examples of amorphous solids are rubber. So take a rubber band and you look on a molecular level. None of the atoms are following any kind of organized pattern. Another example is plastic. Any plastic container, even if it looks like a crystal or it's shaped a certain way, if we look in on a molecular level, the atoms are not arranged in any kind of pattern. And then also what's called asphalt. So anytime you've ever been driving on the road and then you see them pouring this black substance onto the road, they're heated up and then they let it cool very quickly, and then you're driving over it and your tires take a black stain with it, that tar-like material that they're spreading over it, that's called asphalt. Again, the particles do not follow any kind of organized crystal structure, so it's considered an amorphous solid. The last example of an amorphous solid that we're going to talk about is glass. Glass is not a crystal. Even if you think it looks like a crystal, it is not a crystal. Glass is an amorphous solid, also sometimes called supercooled liquids. So glass is not even really a solid. It's considered a supercooled liquid. It's kind of like the internal structures of glasses are somewhere between a crystal solid and a free-flowing liquid. They don't have a definite melting point. We know that when we heat glasses, they start to kind of bend, right? They start softening, but they don't exactly melt. So people that take advantage of this are called glass blowers. I don't know if you've ever seen any glass blowing before, but usually people will heat up glass to a very high temperature. It kind of brightens up, and once it brightens up, it's kind of like this liquidy texture, and they can sort of blow into it and kind of change its shape. And that's kind of how they make all these different little kinds of glass figurines. Now, one of the major differences between amorphous solids and crystals is that when amorphous solids break apart, they often will shatter, but not in any kind of specific pattern. They always break up into irregular cuts and irregular angles and things like that. That's why if you were to take, say, a glass window, right, and as you're driving on the road and a rock comes and hits your glass window, you can't predict the path that it's going to take. If it was a crystal solid, you might disrupt some of the atoms and then the crack would go all along the plane. But no one's driving around with a straight line crack on their windshield. Instead, the crack always goes in some kind of unpredictable pattern because the atoms are all in random order. There's no specific organization of them for the crack to sort of follow. All right, and that's going to go ahead and wrap up our nature of solids talk.